Our next topic is an application of this logic, the logic we have learned so far is digital logic circuit. Let's begin by looking at a very simple circuit you have seen in high school physics. The circuit looks like this. You have a battery, and then you have a switch here. And suppose you have a light bulb. I'm going to use a meter or light bulb. We know if the switch is open and the light bulb is off, and if the switch is closed, and then the circuit is on, the light bulb is on. However, if we have a bit more complicated circuit than this, if we have two switches, there are two different ways to arrange these two switches. One is arranged in series. So we call this a P switch and a Q switch. And another way of arranging two switches is by put them in parallel. And suppose this is P, this is Q. So if you, this is in series, this is in parallel. So if you look at the behavior of these two switches and the light bulb, you're going to see, okay, by the way, if we, for a reason you're going to see immediately, if we, instead of writing open, we call this to be false. And we call this to be true. Okay, just we rename open as a false and rename close as a true. And then you are going to see the truth, the configuration. We'll say the configuration. If in this case, we have P and Q. If both P and Q are true, and the light bulb, what do you call it? Okay, and by the way, I'm going to use the light bulb. I will call it on to be true, and off to be false. For a reason you are going to see immediately. So if both P and Q are true, that means both switches are closed. Then we are going to see the light is on. So we have true. And if this is false in the first case, that means here is you are true, but this one is false. This is open. One is closed, one is open, of course, is false. One is open, one is closed, it's false. The light bulb is on only if both switches are closed. So FF and UF. Sorry, I think I didn't manage to use space in a more wisely manner. Okay, let's look at this, the parallel switch. And you can easily see that there's a P, there's a Q, there's a light bulb. If this both are true, of course, it's true. That means as long as one switch is closed, and you're going to see the light bulb is on. Only both switches are open, the light is off. And of course, you can see here, if I consider P and Q instead of circuit as Boolean propositions or statement or logic variables, and then what this circuit implementing is an AND gate. Here is an AND gate, and here is an OR gate. And let's move on to the next page. So this inspires us to define Boolean gates. So in the 1940s, 1950s, an electric engineer developed something called the transistors. They developed a much more complicated circuit to implement similar functionality. And instead of using light bulb, they use a voltage to denote the signal. And this is the basic idea because before that, people use called analog circuit. So let me write. And what we are talking about is digital circuit. So the big difference between analog circuit and the digital circuit is, for digital circuit, the voltage or the signal is discrete variable. In this case, we have only two possibilities. One is called high, the voltage is high, and the other is low. And in electrical engineering, instead of using true and false, they use 1 to denote high. In our notation, it's true. So I hope from now on you should get used to the notation that we are going to use this, probably use this two notation interchangeably. That means a true and a 1 and 0 and the false. This is a true, this is a false. Okay. We will use this interchangeably. And this is called bits. Abbreviation for binary digits. And for analog circuit, the signal is continuous. And you're going to see something like a sine wave, cosine wave, and the signal can take continuous, can take values in a continuous range. It seems at the beginning you will find that the analog is more powerful because it seems to contain more information. However, it's not as easily manageable as the digital circuit, because digital circuit we can make the circuit can be manufactured and can be augmented in a standard way, and so that we can use this digital circuit to represent the analog circuit more efficiently. Okay, instead of using this, okay, we can represent our previous two examples of circuit as a black box. We have P and Q. This is our circuit configuration. The switch configuration. And here we have a light bulb. If you remember, and we can, this P and Q can be on and off. P and Q can be taken true and false, and the light bulb can be taken true and false. And we will consider this as a gate. And in general, we are going to have probably more than, maybe there's a P, Q, R, S, and finally you have this T, and this is the input signals. And this is the output signal. And now, instead of looking at investigating what's going on inside this black box, inside this circuit or transistor, we just consider this as a black box. And what does that mean? That means we don't care about what's inside, how the inside is constructed, how the inside, how this box is built. We just care about the behavior. That means we just care about the input-output table. It's pretty much like our truth table. So for example, if I write P, Q, and S, so you may have something like this. Remember, this is output. And then we have this 1, 1, 1, 0, 0, 1, 0, 0. This is 1, 0, 0, 0. This corresponds to the first circuit. If you consider S as the light bulb, and you are going to see that the light bulb is on only if both P and Q switches are on. And now we abstract this as a black box. And as a black box, we don't care about the implementation inside the black box. We only care about input-output table. As long as your P, Q, and S behave this way, I will consider they have the same functionality. And because of such a building block is so important, we are going to give them special names. They're called gates. And the basic gate, there are three, maybe to next page. So there are three basic gates. Probably you have heard about them. Is NOT gate, AND gate, and OR gate. Before that, let me first introduce what was called Boolean variables. Boolean variables are 0 and 1. They just correspond to our truth, false, and true. So as I said, from now on, you should think whenever you see 0 and 1, consider as a Boolean variable, then they are just false and true. So the first one is NOT gate. NOT gate, if you NOT gate, you have only one input variable. And the symbol is like this. It's a triangle, and output. The base is the wire connecting to the base is the input, and the connecting to the vertex is output. Input here, output here. So if you use P, so we can think about the P as a logic variable, and also we can think about the Boolean variable. So so R is not P. And not P, by not P, what does that mean for Boolean variable? That means your input is 0, then you get 1. Your input is 1, you get 0. And in electrical engineering, I think this is called inverter. And the next one is AND gate. You have PQ and R. AND gate. The input-output table of AND gate is just what we draw on the previous page. Okay, basically R equals P and Q. And the next one is OR gate. P, Q, R. This is OR gate. This is NOT gate. This is R equals P or Q. And the truth table or the input-output table is P, Q, R. And if 0, 0, then you get 0. 0, 1, you get 1. 1, 0, you get 1. 1, 1, you get 1. You probably notice that I'm switching the order, and this is just my convention, and many people probably use the same use other convention that I start from 0 and down to 1. But for truth and the false value, I start from truth. It doesn't matter as long as you have these four rows. The ordering doesn't matter. And another way to write, I just want to tell you some other way. People use, if you look at textbook or other textbook or papers, and people use, sometimes use this one. So this is NOT gate. The wire is an input wire. For example, this is input wire, and this is output. And then people use this AND gate. This is input, and output is X and Y. And OR gate, write this circle with this OR symbol inside. Okay, let's move to next page. So from this Boolean circuit and and Boolean variables, we can construct a Boolean gate. I'm sorry, Boolean gate and Boolean variables, input variable. You can construct a Boolean circuit. Sometimes people call this CKT to denote circuit. And for example, how do we? Let me give you an example. How to implement XOR using AND or and the NOT gate. So remember, if I want to build XOR gate, if this is my input P and the input Q, and the output R should equals P XOR Q. So the question is, if you have input P and Q, how do you implement? How do you build a black box inside, and so that the output R equals P XOR Q? So what we can do is, so first let's see what happens if I just simply output P or Q. What's wrong? P or Q is the same as P XOR Q, as long as P and the Q are not all true, or all P and the Q are not all one. So if P and the Q are all one, then we have to output 0 instead of output 1 for the OR gate. So what we can, so therefore what we can do is like this. We use an OR gate, and then we use another AND gate. So what we want is, we want to say, we want X AND of this one. So we want to say whenever P and Q is 1, we want output 0. So therefore I use the negation. And then finally, I output the AND of these two variables. Okay, now you can easily check that if P and Q are not all 1, then what I'm going to output is, because if they are not all 1, and if I call this T, then T is 0. Because T is P and Q. If not all 1, then T is 0, and not T is 1. And therefore, if you take an AND gate of this, you are going to see, you are going to output this, basically output P or Q. And if if P and Q are both 1, then this T is 1, and not T is 0. So because you AND this 0, you're going to output 0. So what we are saying here is basically your black box look like this, and this is your P and Q, right? And so you first connect OR gate with this two input, and then you connect them to also to a NOT gate, and then to a negation gate, and finally an AND gate of this you output. Another example, let me call this example 1. Another example, let me just show you the power of this circuit. Is example 1 is how to implement addition. Implement 1-bit adder. So what I'm saying adder is, if I have 1-bit X and Y, if I do addition, so what do we get? You can, because it is binary, and what we are going to have is, let's call this Z. So if 1 is 0, if X and both X and Y are 0, so what should XZ look like? X, Y, and Z. So if both are 0, then I should output 0. If one is 1, I should output 1. But what if both are 1? I should output 0, but I have another carry, which should be 1. So that means X 0 plus 0 equals 0. 0 plus 1 equals 1 plus 0 equals 1. 1 plus 1 equals 0. But the carry is 1. And for these two cases, carry is 0. Okay, and from here you can see that we need to implement two-bit input. Sorry. So we have this X and Y. We have 2-bit input, but we have 2-bit output. And this is the sum, okay. And this is called carry. And if we have multiple bit, this carry should be added to the more significant 1 bit, the bit to the left of this bit. Okay, so how do we implement sum? Actually, we have done this before. We have done this already. This is nothing but XOR gate, right? Because the sum is just, you can see it's just XOR. 0 XOR 0 equals 0, 0 XOR 1 equals 1, 1 XOR 0 equals 1, 1 XOR 1 equals 0. Or what about the carry? And the carry is nothing but AND gate, right? Because carry is 1 only if both X and Y are 1. Okay. So before we end this discussion with this section, I want to mention that NOT gate, AND gate, and OR gate are called universal, a set of universal gate. So what does that mean? That means using NOT gate, AND gate, and OR gate, and with only these 3 kind of gate, we can basically implement any function. Okay, I'm not going to show why this is true, but if you are interested to see answer, please let me know. And before we leave for this video, and for this video, let me mention that there are 2 other kind of apart from XOR gate. There is a NAND gate. A NAND gate is AND gate negation of AND gate. And another NOR gate. Negation of OR gate. So why we care about these 2 gates? Because these 2 gates are have very nice property. This NAND gate itself is a universal gate. That means basically you can use only one type of gate, namely NAND gate, and to implement any function. And the same thing holds for NOR gate. And I'm not going to give the proof here, just let you know that you know this fact. Oh, sorry, I think I didn't. Okay, not too late. So the NOR gate, AND gate, and OR gate. So NAND gate, negation of AND gate, NOR gate, and negation of OR gate. So both, maybe it's confusing. So universal. and you shouldn't be aware of this fact. So NOT gate, AND gate, or OR gate, each individual gate, individual type of gate is not universal. Okay, they have to, these three combined together, they form a universal set of gates. However, for NAND gate and NOR gate, each of themselves is a universal gate. Okay, I think I'm going to stop here for this video. Thank you.